Hello everyone, welcome back to chapter 1. Today is part 3 of chapter 1. We will take a look at the definition of the fundamental dimensions and the dimensional analysis, part of the last um, portion of this chapter 1. So, dimensions of the quantity are the base units that make up. They are generally written using the square brackets. So for example, the three-dimensional units used in the physics are the length, time, and mass. Their units L, T, M. They normally put it into the bracket. Any and every physics unit is expressed with the combination of these three fundamental dimensions. For example, speed equals to the distance divided by time, and its dimension is L over T in bracket, as you can see here. So quantities that are being added or subtracted must have the same dimensions. In addition, a quantity calculated as the solution to a problem should have the correct dimensions. So if you use this dimensional consistency, you can actually check that any given equation in physics are correctly defined based on the rational expression, or if those physics are actually is incorrectly defined. So dimensional analysis is the checking of the dimensions of all quantities in an equation to ensure that those which are added, subtracted, or equated have the same dimensions. For example, let's take a look at the basic physics equation normally used for the speed of object. So this is just example to see how dimensional analysis can be used to find out if equation actually is just correct or not. So this is just a given equation, and by using this dimensional analysis, we'll take a look at this equation is correct or not. So here, the definition of V is L over T, length divided by time, and here V naught is the same, L over T, and the number doesn't have a unit, so you can ignore it, but acceleration is length divided by time squared, and you multiply time squared to the acceleration, so time squared cancel each other and only leave the L. So as you can see, L over T plus L does not have consistency in their definition of unit, and they are also not consistent with the left hand side. So you can see this equation actually is incorrectly justified. So by simply just comparing the unit, you can easily actually find out the equation is correct or not. So that's this simple way, just used a lot in the physics, because it's just very easy way to find out the given quantity in the equation is correctly expressed or not. Let me summarize chapter 1. Theories are created to exploit observation and then tested based on their prediction. A model is likely an analogy. It is not intended to be a true picture but to provide a familiar way of envisioning a quantity. A theory is much more well developed and can make testable predictions. A law is a theory that can be explained simply and that is widely applicable. Dimensional analysis is useful for checking calculations. Measurement can never be exact. There is always some uncertainty. It is important to write them, as well as other quantities, with the correct number of significant figures. The most common system of units in the world is SI system. When converting the units, check dimensions to see that conversion has been done properly. Although the magnitude estimates can be very helpful. Here, observation would be the first important step toward the scientific theory. It requires imagination to tell what is important. And theories are created to explain observation. They will make predictions. Observation will tell if the prediction is accurate. And the cycle goes on and on and on. So no theory can be absolutely verified, although a theory can be proven false. Um, then how does a new theory get accepted? Well, first of all, prediction agree better with the data, and they explains a greater range of the phenomena. Then, for example, Aristotle believed that object would return to a state of the rest once put in motion. Galileo realized that an object put in motion would stay in motion until some force stopped it. So the early days, the Aristotle's theory was accepted as absolute true, and people believe that theory is always true. But later on, when people find out there's some error in that theory, the exceptional case was found, and they start to just try to find uh, the why, try to find the why there's exceptional cases existing, and then try to just generalize that theory with the more actually more standard model of theory. So basically, based on the scientific experiment and scientific measurement, it turned out the Galileo's theory is actually actually true and accurate than more accurate than Aristotle's actually original theory. So since then, Galileo's theory is just basically accepted to the people. Now let's go through the appendix of chapter 1. Um, the principles of physics are used in the many practical applications, including the construction. The communication between architects and engineers is essential if disaster is to be avoided. Um, what you see in this picture is the Roman aqueduct, which was built 2,000 years ago. That is in the left hand side, and it was just a steel stand. So that original the, the architecture is just designed based on the true science and the really well designed actual infrastructure. But the other structure and the other images in the right hand side, it shows the Hartford Civic Center that was collapsed in 1978, just 2 years after it was built. So it clearly indicates the poorly designed structure based on false engineering can create and can cause catastrophic outcome. The models are very useful during the process of understanding phenomena. The model creates mental pictures. Care must be taken to understand the limits of the model and not to take it too seriously. The theory is detailed and can give testable predictions. A law is a brief description of how nature behaves in a broad set of circumstances. A principle is similar to a law but applies to the narrow range of phenomena. There's two different definitions of the justify the physical quantities, like accuracy versus precision. Accuracy is how close the measurement comes to the true value. Precision is the repeatability of the measurement using the same instrument. So it is possible to be accurate without being precise and to be precise without being accurate. So there's a way to estimate physical quantities uh, by just rapid evaluation procedure. What you see here is the one of large lakes in the Sierra Nevada of California, and now we want just to estimate the amount of water in this lake. What would be the easiest way? So basically, we can maybe imagine that water is contained in the very simple model, like cylindrical model. So let's assume that all the water in within this small, I mean this cylinder, this size of cylinder. So here normally, if you think of this water reservoir with the tank 1 kilometer diameter, and the depth might be 10 meter, then you can easily just estimate the amount of the water possibly in this lake. So the volume of this cylinder is, see, pi r squared times depth. So r is 500 meters, so the pi times 500 meter squared times 10 meter. So the volume is about 10 to 7 cubic meter, which is probably 2,200 pounds in weight, because the density of water is the same as 1,000 kilogram per cubic meter. So you apply that ratio, that means the density to the volume of water, and you can estimate the amount of water in this reservoir or in this lake. So this is called the rapid estimating. So Next example is the radius of the Earth. Um, if you have ever been on the shore of a large lake, you may have noticed that you cannot see the beaches, piers, or rocks at water level across the lake on the opposite shore. The lake seems to diverge out between you and the opposite shore, a good clue that the Earth is round. Suppose you climb a step ladder and discover that when your eyes are 10 feet, maybe 3 meters above the water, you can just see the rocks at water level on opposite shore. From a map, you estimate the distance to the opposite shore as d equal to 6.1 kilometer. And use the h, the height of your head, the top of the head is 3 meters above the ground. Then to estimate the radius of the R of the Earth. So using the triangle formula, so if you assume Earth is perfect sphere, then the radius is given by the R, and applying the triangle formula can easily actually just calculate the R from that ratio. So here h plus R square should be equal to d square plus R square. From this formula here, h is the height of your eye from ground, R is the radius of Earth, and d is the diameter of the lake. So from here, R should be d square minus h square over 2h. Here AD is 6.1 kilometer. H is 3 meter. So R must be 600,200 kilometer roughly. So this is just a rough estimate. It gives us some, approximate numbers of the physical quantities. So even without precise measurement, by using the object around your physical quantity of your interest, and you can actually estimate the actual numbers. So this is the end of the chapter 1, and I thank you everyone just actually just watching the end of this just video, and hopefully you can stay with me next chapter, so we can continue on our physics journey, part of our class. Thank you, and hope to see you all in the next video.